So welcome back to Physics of Music. Last time we were talking about interactions between objects and how when you have these interactions, then the velocities or the momenta of objects can change. And we introduced the concept of force. And the idea was that the force is a way to quantify the strength of one of these interactions, the strength of a push or a pull at some instant in time. And the idea was we could see how strong a push or a pull we have by looking at how quickly the momentum of the object changes with time, or the rate of change of momentum. And our basic relation was that the strength of a force is equal to the rate of change of momentum it produces. And we said that for the same force, for the same kind of push, regardless of what object that you're pushing on, the same push will result in the same change in momentum. So this basic relation between forces and the rate of change of momentum is the content of Newton's famous second law. What I said last time is that the most useful version of this, or the way that I like to think about it, is really relating the rate of change of velocity, so that is the rate of change of momentum divided by mass. It's relating that to the force. So we get rate of change of velocity in some direction is equal to the force on your object in that direction divided by the mass. And this form of the equation is very useful because it emphasizes that it's something that will allow us to predict how something is going to change with time. It'll allow us to predict what the velocity is at a future time, knowing what the velocity is now and knowing what the forces are. So we did one example of that last time, but I want to do some more examples today and then talk more generally about how we can use Newton's law together with a definition of velocity to make all sorts of predictions of how positions and velocities of objects will change with time. So just before we get into that, I want to talk a little bit about what kinds of forces are there when we're going to apply this equation. We usually have an object in some environment and we want to understand what the various forces on that object are. So let's talk a little bit about what some of these forces are that generally apply in everyday situations. And so the first thing that a lot of people will bring up is the force of gravity. So this is a very familiar force here on Earth. If I have an object, I could have that object be stationary by holding it here, but if I let go, it immediately starts moving in the downward direction. So its velocity downward is changing with time, its momentum is changing with time, and so we can conclude that there's a force on it, and we call this the force of gravity. This is something that we're going to talk about in detail in the next slide. What other kinds of forces? Well, there's all sorts of things, like pushes and pulls and all kinds of things where you have various objects kind of directly interacting with each other. So an interesting thing is that fundamentally, most of those, other than gravity, most of those forces actually have to do at the microscopic level with this electric force, the basic force where charges repel each other, like charges repel each other and opposite charges attract each other. And so when my hands come together and push each other, really what's happening is that at this microscopic level, there's a bunch of electrons in my hand and they're negatively charged. And when I bring my hands together, well, those electrons are getting really close together and they don't really want to be so close together. And so there's this repulsive force. And that's really where the pushing force is coming from. When I push something, or similarly, when you pull something, if I pull on a rope, what happens is that actually there's some attractive forces inside the rope between the positive charges and the negative charges. And if I pull on the rope, then those get a little bit further apart than they would want to be. And there's this attractive force. So a lot of your everyday forces are actually coming from ultimately from these electric forces. We also know that there are these special kind of magnetic forces that you have between two magnets. We'll probably talk more about those later when we try to understand some musical electronics. Other kinds of forces, well, you have forces of friction. So when something is sliding across the table, it doesn't keep going forever. It tends to slow down. That has to do with the roughness of your object and the roughness of the surface. Ultimately, again, that has to do with like electric forces between the various atoms and molecules of your objects. You have something like a compression force. If you compress an object like a spring, or even a solid object like a brick or a piece of wood, if you compress that thing, then there's some force that it pushes back with. Again, that's because all the charged particles in the object don't want to be so close together, and so they push back. An interesting version of that is the thing that we call the normal force. So when you have an object sitting on a table, I'll just have it sitting on my hand, then there's this force of gravity downward, and so we might think it would accelerate downward, it should start falling, but it doesn't, and that's because there's some upward force from the table, or in this case from my hand. And where is that from? Well, that also has to do with a compressive force, where you compress like the table that the thing is sitting on, and then the table is pushing back because it doesn't want to be compressed, and that holds the object in place. Okay, so there's many different forces. There's some even that we're not familiar with in everyday life, but operate in an important way inside atoms, inside the nucleus of atoms. So that people talk about the strong force and the weak force of nature as being fundamental forces. Just to give you an example of how we know there's a strong force, if you think about the nucleus of some atom, you've probably been taught that this is composed of protons and neutrons, and that protons all have a positive charge. And so it's interesting to think, well, how is it that all those protons with these positive charges want to be so close together in the nucleus when like charges repel each other? And so the answer is that there's the strong force holding those things together, the protons and the neutrons, and that's even stronger than the electromagnetic force that wants to make the protons fly apart. All right, so that was just a general discussion of various kinds of forces. There are probably more that we didn't mention, but the general thing we're going to want to do is then to understand quantitatively how strong are these forces in various situations. And once we know that, then we can basically predict everything that we may want to predict. Okay, so once you know how to calculate the forces, then that allows you to figure out the rate of change of velocity using our Newton's law formula, and the velocity tells you the rate of change of positions, and then you're all set. And so we're going to see lots of examples of this today's class and next class. Okay, so let's start with an example which has to do with the force of gravity. And so as we are all familiar with, the force of gravity is a downward force that acts on any object that has a mass. And in the environment of near the surface of the Earth, the force of gravity, we say it's proportional to the mass. So you just, to find the strength of that force, you just take the mass of your object and you multiply it by this number, which we call g, and which is 9.8 meters per second squared. The thing works the same way if you went to the moon or Jupiter or some other planet, you get the same formula, but this number would be a little bit different. Okay, so we're going to now apply this and do a calculation of predicting how a velocity changes. So here's a really simple example. You have an object. It's a happy object as usual. It's moving upward at 3 meters per second. And what I want to know is what will be this upward velocity after 1 second. So it's a good place to stop the video and just try to work through that and see if you get one of these answers. Okay, so now let me talk through this. And so to do this question, we're just going to use these two basic results that I mentioned in today's class. The really essential, important formula that we're always going to use to predict how velocities change is this Newton's second law formula. It says the rate of change of velocity is equal to the force divided by the mass. In this case, the force is coming only from gravity, and so it's a downward force of m times g acting on our object. And so using these two formulas together, we learn that the rate of change of velocity is going to be the mass times g, or 2 kilograms times g, but then we divide by 2 kilograms in order to get the rate of change of velocity. Okay, so g here, this number g, is actually going to be, in the end, the rate of change of velocity for our object. Okay. So this is in the downward direction. And so we would say the rate of change of the upward velocity is minus 9.8 meters per second squared. Okay, so let me just, there we go. So the upward force is negative, and the rate of change of upward velocity is F upwards over m, which is minus g, or minus 9.8 meters per second squared. Okay, so now that we know the rate of change of velocity, we can then predict how much the velocity changes in 1 second. And so we multiply that minus g by 1 second, and that gives us the change in velocity during this time. And that then is minus 9.8 meters per second. Okay. So it's the same number as the rate of change, but that's just because our time was 1 second. Had it been 2 seconds, the velocity would change by minus whatever twice that is, 19.6 meters per second. And so finally, we want to know what is the upward velocity after 1 second. And so we just take the velocity that it was before, so that's 3 meters per second. And then we add to this the change in velocity, which is minus 9.8. And the total then is minus 6.8 meters per second. Okay, so that is the upward velocity after 1 second. And the negative sign just indicates that, in fact, this thing is moving downward at a speed of 6.8 meters per second. Okay, so let me summarize then so far what we've got that helps us predict how things change with time. We had the basic formula, which is the definition of velocity, that the rate of change of position in some direction is the velocity in that direction. Okay, so if I know the velocity, that's equivalent to knowing how quickly the position is changing. But now we also have a formula that tells us the rate of change of velocity in some direction. And to get that, we just take the force in that direction and divide it by the mass. In that simple example we just did, the force was just the same regardless of where the object was and regardless of its velocity. But in other examples, what you'll find is that the force might depend on the position of your object relative to other objects, or it might depend on the velocity. So we're going to do an example like that later on in this class. So what I want to emphasize is that these two things together really allow us to take our position and our velocity now and then figure out what they're going to be in the future. And to kind of emphasize that, I made this diagram here just to really visualize what these equations, what this physics is doing for us. And so you could think of this procedure that we just did and that we're going to do in more detail in the next question as something where we take as inputs the position of an object at the present time and the velocity at the present time. And then we decide how far into the future do I want to look. Then we do a procedure, we turn the crank, and after we're done, out pops the position of the object and the velocity of the object at this future time. So let's break down how that works in general And so we're going to basically open up this machine and see what's inside. Okay. So I'll do this step by step. So we start with the inputs, which are the position now and the velocity now. And the first thing that we can figure out is what this future position is going to be. So we use that the velocity tells us the rate of change of the position. And so to get the change in position in this amount of time t, we just take that rate of change of position, we multiply by the time, and then that will give us the change in position. And then we add that to the original position to get the new position. So I just want to emphasize that in doing this, we're kind of assuming, well, we are assuming to make sure that this is an accurate answer, we're assuming that the velocity does not change very much during this time step. And I'm going to talk about later, well, how we can get around this. But for now, what I want you to imagine is we want to make this time step small enough so that the velocity is approximately constant during this time. Okay, so obviously if we have the ball going up and we take the time step to be 0.00001 seconds, then the velocity is going to be pretty much the same throughout that entire time. And then it'll be very, very accurate to say that the change in position during that time is just the velocity times the time. Okay, what about predicting the future velocity? Well, we also now know how to do that. So you take your position now, you take your velocity now, you look at the environment of the object and use all of that information to calculate the present force on your object. Taking that force and dividing by the mass gives you the rate of change of the velocity. That's what Newton's second law says. And so then to find the change in velocity during this time, we take that rate of change of the velocity, we multiply it by the time that passes, and that will give us the change in the velocity. And then we just take that and add it to the previous velocity to get the new velocity. So as I said, simply doing this multiplication, that the change in position is equal to velocity times time, the change in velocity equals the rate of change f over m times time, that assumes that these rates of change are remaining constant. And in order to ensure that, what we want to do is take this time step to be very small. Small enough so that v and f don't change much during that time. But then you would say, well, that's not very interesting. If I can only predict the position and the velocity 0.001 seconds into the future, that's kind of useless. What I really want to know is how things will change 5 seconds into the future, or a minute or an hour into the future. So the nice thing is that all we need to do is just repeat this procedure a whole bunch of times. So this thing works very well to figure out the position of the velocity at a short time into the future, but then we could just repeat and repeat and repeat. So we take the new position and the new velocity and then plug it back into our procedure and then calculate the force again, calculate the new change in position, and so forth. Okay, and then in this way, we can effectively predict the position and the velocity and how they change with time over longer periods of time. All right, so that was a lot of talk. And to really understand this, you need to work through an example. And so what I want to do is leave you with this example. And so, let me just, already wrote some things on here. Okay, so let's clean that up. And so here's the example. I've chosen an example which is probably unfamiliar. It's something where you have a ball and it's moving. We're not thinking about gravity here, so maybe it's in a zero gravity environment, or maybe it's underwater or something. It's just moving at a constant velocity, and the force that's acting on it is a drag force. So that's another way of saying, sometimes we refer to air resistance as air drag, or a ball moving through a fluid, we would have a fluid drag force. Okay, so this is a force which opposes the velocity, opposes the motion of an object. And so when you have objects moving through air or moving through fluids, they tend to slow down because of this drag force. And so what your goal in this question is just to understand what the effect of the drag force is. And the amazing thing is we don't really need to know anything beyond what we already talked about. So this general procedure will work even for this maybe relatively unfamiliar kind of force. And the only thing I need to tell you about the force is how it depends on the position and the velocity of our object. Okay, so this is contained in the formula here, that the drag force on this ball, it is equal to the velocity of the ball, or just the negative of the velocity of the ball, times a constant. Okay, in general, that constant will depend on the shape or the size of the object, but in this case, I'm telling you that this constant is 0.5 kilograms per second, which just happens to be the units that we need for everything to work out to a force here. Okay, so your job is to take the initial position, which is 2 meters, the initial velocity, which is 3 meters per second, and then work out what these things are going to be after 0.1 seconds using the procedure that I just talked about. Okay, so I'm going to end this video here, and then in the next video, I'll go through this in detail so you can see how the procedure works. But I definitely recommend trying to do this on your own and thinking through each of these steps to fill in the various boxes here, 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 and here. And if you want something extra, then see if you can do the same thing for one more time step into the future, which is going to be 0.2 seconds.